Alright, gang, here we go. This is for physics. We're in Unit 7. Part 4, we're talking about sound waves. So we just finished up talking all about sound, how it interacts with things, or we talked about waves and how they interact with each other, how they bounce off of things, all sorts of wave properties, frequency, period, blah, 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 so many things. Now let's talk about some practical applications of waves. First one we're going to talk about several, is sound. Okay, sound, you've been hearing sounds for a while. You're hearing my voice now. You're welcome. Okay, and so you, so you get to, we're going to learn about sound. All right, so here we go. What is sound? Sound is a longitudinal wave. Remember that, whoops, I forgot to turn on my little talker, or my thing. Okay, so sound, longitudinal wave. That means we've got these two areas to a longitudinal wave called the compression and the rarefaction, right? The compression is the part where the thing that you're pushing, your medium gets squeezed together and its density goes up, and then the rarefaction is when it gets spread out and its density goes down. All right, so all sound waves are produced by vibrating objects. Okay, so tuning forks in class we've probably played with. We'll play with tuning forks quite a bit, right? You hit them, tuning forks kind of look like this, right? They look like this, and they come up, and then they kind of make a fork shape that you'd never actually want to use. But anyway, so you'd like whap it, and then it buzzes, it vibrates so fast that it's creating a specific pitch. Okay, guitar strings, vocal cords, like if you I suggest looking up a YouTube video where they stick the microphone or the not microphone, a video camera down somebody's throat and actually look at the vocal cords while they're singing or playing or talking and stuff like that. And it's actually pretty bizarre what it looks like. It's like we're all really just aliens kind of thing. Okay, and then speakers, like the speakers you're listening through, is really just the speaker is just vibrating really, really fast, and it's pushing air against your ear, and you're hearing me. Okay, the vibrating object pushes the air, forming compression, then spreads them apart, forming that rarefaction. All right. So here, this video here, and I suggest looking at this video. It's pretty good. Okay, and it's a slow-mo video. Okay, and what they've done is they took a tuning fork, and then they started it, and then they buzzed underwater. I took the screen cap right here, and like you can actually kind of see in the waves where the tuning fork is. Okay, you can see the start of this longitudinal wave. Okay, you can see this compression, rarefaction in action. Okay, you can see this waves of where it's starting. So that's pretty wild, and you can actually see how much energy this tuning fork is putting in. When this is in slow motion, they do it, but when they do it in fast motion or in real life motion, okay, non-slow motion would probably be best. Like they stick it in the water and it goes and splashes everywhere. It's pretty cool. All right. Graphing sound waves. Well, how do we graph sound waves? Well, if we're going to graph it as a longitudinal wave like it actually appears, it would look something like this. Okay, the dark regions are compression and the light regions are rarefaction. Okay, now this is helpful, right? We can measure the wavelength, right? Pretty easily. The wavelength would be from one compression to the next, right? So from there to there. So that there would be one wavelength. Okay, so that's kind of nice, right? So, but what's even easier, okay, is if we graphed it on a graph and just put density here on the y-axis, okay, we could say, well, when we have a compression, we have a high density, we have a rarefaction, we have a low density. And then we can compare, we look, oh, it's not like a straight change, it's kind of like a curvy. It starts kind of darker blue, and then it suddenly becomes lighter blue. So we get this hilly shape, and oh, well, look at that. It looks just like a sine wave, which is exactly what we used to graph transverse waves before. All right, so really when we graph longitudinal waves, we can look at them like this, all right, but we can also look at them like this, all right? So characteristics of sound, all right? Frequency, remember, is defined as the number of waves per second, all right? Number of waves per second, we use hertz, right? And that's really equal to 1 over seconds or a second inverse 1. All those things are equivalent. Okay, so you have heard of ultrasound. What is it? Well, ultrasound is sounds above the frequency of human ears, okay, or the range of human hearing. Okay, frequencies audible to humans are between 20,000 and 20,000. Now these are 20 hertz and 20,000 hertz. Okay, 20 hertz and 20,000 hertz. Now this isn't like a dead set number. These are averages. Okay, most humans can hear between 20 and 20,000 hertz. Sure, there's the freakazoid out there that can hear it like 5 hertz and 50,000 hertz. But for the most part, 20 to 20,000 hertz. Okay. Just to give you an idea, if you hit a middle C on a piano, it's at like 262 hertz, or exactly 262 hertz. If you're playing an orchestra or a band and you're tuning, that concert A is at 440. So if you ever heard of the term like A440 or anything like that, that's the hertz or the frequency of that note. Okay. Emergency broadcast signal is at 1,000 hertz, so that's that's at 1,000 hertz, nice and pleasant. Okay, infrasound frequencies are any frequencies lower than 20 hertz. Okay, so the infra means below. Okay, so it's below sound frequencies is essentially what this means, and then ultrasound frequencies are greater than 20 hertz. All right. Now pitch, now this is an interesting idea. You'll find as we move through this section about sound that there's several times where we take a second and be like, yeah, we learned about the science way of talking about things. But really, humans have been dealing with sound for ages and ages and ages. And so there's parts of human vocabulary or human perception that play an important role when we influence sound and when we think about sound. And pitch is one of those things. Okay, pitch is how we talk about how high or low a sound as it appears to be. Okay, essentially, pitch, okay, is your ability to measure frequency on your own. Granted, you can't assign it a value unless you practice a lot and get develop perfect pitch. Okay, but you can tell, your ear can tell what frequency it is purely based on, oh, that sounds like a higher note, that must be a higher frequency. Okay, so primarily your pitch is determined upon those things, but it also depends slightly on other factors. For example, and this is kind of a big one, especially if you're a flute player or violin player playing very high notes, okay, oboe, stuff like that, you pay attention here because higher frequencies, okay, so the high notes appear to have a higher pitch when played loudly, even though the frequency does not change. So that's pretty wild. Okay, so you could be playing based on a tuner, you could be playing the right note, but people listening to you might hear it sharp because it actually appears to have a higher pitch than it actually does, just because of the way the human ear works. So then it's kind of this hot debate. Well, do you play it on the right frequency because that's what the right thing is scientifically, musically, or do you play it bend it down a little bit to counteract this tendency for us to hear it sharp? Just because music is meant to be listened to. I don't know. So it's kind of one of those things. Where do you lie on your musicality? Me personally, I kind of flip-flop. It kind of depends on what you're trying to accomplish with what you're trying to do. I don't, Anyway, it doesn't really matter. So we can talk about it some other time. Okay. Speed of sound, though. Sound waves travel through solids, liquids, and gases. This makes sense. Everybody's, put their head on their table, and then the teacher walks by to wake them up by knocking on the table, and you can hear the knock through the table, right? If you've ever been underwater and tried to talk to your friend, you've heard their voice. So you couldn't understand them, but you've heard their voice, right? So sound waves travel through solid, liquids, and gases. So in which would the speed generally be greatest? Why? All right, I'm just going to jump ahead here. Solids have the fastest, and the reasoning is because these molecules are more closely packed together. Okay, so the particles respond more rapidly to compressions. And that makes sense, right? We just talked about how longitude waves, right, are really caused by one thing hitting the next, hitting the next, hitting the next, hitting the next as they go across like this, right? Now, if these molecules are really close together, then this motion, this passing them on, can happen a whole lot faster. Okay, so in a solid, that gets passed a lot faster. Okay, which is why if you've ever done like the cup and the telephone thing, okay, if you've ever gotten a really, really good one where you and your friend are like 25 feet apart from one another with two styrofoam cups and a string, you could have noticed, had you been old enough to pay attention to or known to pay attention to it, you would have noticed that you could actually hear his voice sooner, okay, through the cord, all right, of the string connecting your thing than you would have had he just talked to you normally. And that's because it travels through that solid string faster, okay? Now, on the other side, temperature, how would that affect the speed of sound waves and why? Now, there's two schools of thoughts here. You're probably thinking to yourself, well, if we just talked about density, and density is important, let's think about it this way. Okay, so if we're at a high temperature, that means we're at a low density. Hot things rise, right? So the hot air would rise, so that means it's less dense. Okay, so that means the speed of the sound must go down, right? Because they're farther apart. However, on the other hand, at a higher temperature, those molecules are moving much faster. So if they're moving much faster, they would have more collisions. So we could go into depth into the mathematics and maybe some experimentation in order to figure out which one affects more. But we're just going to jump to the chase here. And the fact of the matter is is that the higher temperature increases the speed of the waves because the particles are moving faster and colliding more often. So it actually turns out that the speed of the waves at a higher temperature makes more of a difference than that slight change in density. And think about it this way, like the difference in density between a solid and a liquid and a gas, or solid and a gas, is drastic, right? Especially gas to solid. Like I can't put my hand through my table, but I can put my hand through this air all the time, all day long, right? But I can't stick it through this table. Okay, and so that density difference is huge, right? It's a drastic change in density, so it has a big effect on the speed of sound. However, if you're raising your temperature 10, 15 degrees, it's not really going to change the density of your air very much. However, the kinetic energy of your molecules will go up quite a bit. All right, so that's why the air temperature affects it more, because the kinetic energy has gone up and these molecules are moving faster, therefore they collide more. All right. So here's some examples of speed of sound. All right, you've got speed in various media, like air at 0 degrees Celsius travels about 331 meters per second. 25 is about 346. All right, 366, etc. And we'll actually do a lab where we can measure the speed of sound. Oop, not at 100 degrees. We're going to do it at room temperature because we're lazy. All right. Notice here, though, I think this is pretty interesting, that seawater versus water. Okay, sound travels about 100 meters per second faster in seawater, and that's because of the density of seawater. Seawater is more dense because of the salt. Okay, keeps all those water molecules closer together because there's more intermolecular forces. Notice how fast it travels through these solids. Aluminum and copper and iron, super fast compared to the gases. Okay, a couple more things here. All right, all waves propagate in 3 dimensions. All right, when I'm talking, my microphone's picking me up here. My wife and family is probably picking me up there. Okay, if somebody was behind me, they can hear me. Okay, freak me out for a second. Okay, and then anyway, so you can hear sound propagates in all 3 dimensions. Okay, that makes sense, right? So essentially these waves of sound go out as spheres, one direction in all the ways. Okay, and so we've got this diagram showing how waves propagate. Okay, these blue circles are known as wave fronts. Okay, wave fronts. Those are what they're called, wave fronts. They're the blue circles. Essentially, they're representing the crests of your wave. Okay, they're the crests. All right. So it would look like something like this. Oops. So it would look like this. Oh my goodness, it's doing it like this. Okay, crest to crest. So that's a wavelength, right? So the distance between 2 of them is the wavelength. These rays, these red arrows here, okay, they're pointing where our graph is going, okay, or where our wave is going to. Okay, so essentially they always just point away from the source, okay, the direction of propagation. All right. So the question is, how would these wave fronts appear if they were much farther from the source? Okay. Well, the farther you are from the source, these wave fronts become more nearly parallel at great distances. And think about it this way. So if I had, how do I do a blank? Here it is. Blank white screen. Pointer options. I was hoping I could make a circle. I guess I can't. All right, here we go. So if we've got some source right here, right? And that source, the waves are propagating. So we're going to draw some wave fronts as we go out, right? Okay. You're going to notice that I'm not very good at drawing circles. All right. And then we're going to keep going. Okay. Keep going. All right, keep going. All right, keep going. Keep going. So notice as I get farther away from my source, these wave fronts are becoming more like straight lines. Okay, become more and more nearly parallel to each other. Isn't that pretty wild? Like you can imagine, like these guys would still curve up and around, but during that segment right there, they're pretty much straight up and down. Okay, and so the idea is that when you're far, far away, you don't really think about them in these circles like we do when we're close to the source. You think of them more as plane waves, right? They're just straight, flat waves like you do in geometry. Remember, planes in geometry is a flat 2-dimensional surface, all right? Okay, and so anyway, so that's how we kind of think about it. Last thing here, okay, is known as the Doppler effect. You've probably heard about this before. This is the effect that makes it as your car, NASCAR cars go around, and as they come around the circle at you, they kind of go meow, 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 like that. Okay, and so what essentially happens is that these wave fronts, if somebody is producing a constant tone or constant frequency and they're moving towards you, the wavelengths tend to go down. Okay, the wavelengths go down. Now, because the speed has to remain constant, but the waves go down, okay, that means that these frequency that you observe goes up. Okay, so for example, here's an ambulance. All right, this ambulance is producing its siren, and there's one person listening to it here, one person listening to it here. Notice that these wavefronts in the direction the ambulance is going, these wavefronts are a lot closer together. The wavelength is a lot lower, so therefore the frequency has to be very high for observer A. Vice versa, okay, observer B, okay, these wavelengths are a lot longer, so that means he has to have a very low frequency for what he hears from the sirens. And that's why when a siren kind of passes you, it kind of goes wheel, 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 wheel. And it kind of gets up as it comes back, and it goes back down. All right. And so it all depends upon the motion of the observer and the motion of the person that's on it. So if a person that's riding in that ambulance listening to the siren, the wavelengths aren't going to change. It's just going to sound like wheel, 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 just like normal old siren. Okay. Another wild thing to think about with siren, or with the Doppler effect, is primarily we've thought about it in terms of sound because that's an easy way to think of it. But the Doppler effect also affects all other types of waves. Importantly, it affects electromagnetic waves. So like a satellite that's orbiting the Earth, okay, people that communicate with that satellite, if they're stuck on the ground and the satellite comes by like this, when the satellite is coming this way sending radio waves to talk to the people at the base, the satellite comes by as it's coming this way, its radio waves are going to be much closer together, right? And so they're going to come in faster. So you have to decode them differently as they come up and over, because then over here, as it's traveling away from the base, those radio waves are going to be farther apart from one another. All right. So it's pretty wild what these things can do, or what the Doppler effect has. It affects lots more things than just sirens and NASCARs. All right. So anyway, so that's it for. You can watch this video. It's kind of pretty fascinating. They go through that whole idea of space stations and so on and so forth. Talking and using or having to worry about the Doppler effect. All right. So that's it for part 1. Okay. Go ahead and do your not part 1, part 4. And let me know if you do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.